in the last class, oh, by the way, if you came in late, make sure you go ahead and send me that text. I still got a couple people signing on. So 513-494-6162 if you didn't save the number. Go ahead and text that number. So in the last class, we talked about a couple things. First of all, I mentioned that even though any data or any information is stored in a PLC or digital device as zeros or ones, how those zeros and ones are interpreted really depends. There's basically two types of data that can be stored in a digital device or in the PLC. And it's going to be a number or it's going to be a code. And so we were talking about the differences between numbers and codes. You know what a binary number is now. Numbers have what you call place value, what computer engineers call weight. So numbers are weighted. They have place values. Whereas codes, some codes have a kind of a position weighting, but most codes, the way you distinguish a piece of data one from another is just by the series of bits. And so this lecture, this discussion that we're going to talk about here for the next couple minutes deals with binary codes. We're going to look at some different codes and the way those codes are represented. And so one piece of hardware that you use with PLCs, and actually there's a couple that use something called binary coded decimal. So there's a couple devices that you would connect to a PLC that uses a code called binary coded decimal. And probably the most familiar one that you've come across will be the one I'm showing you now. And these are everywhere. This is called a 7-segment display, but you probably call it a LED, a light emitting diode, LED. And then we talked about the LED display. We talked about the LCD display. Basically the same kind of thinking, just different technologies. Liquid crystal display and LED is light emitting diode. Two different technologies that do pretty much the same thing. But if you zoom in on this top diagram, it's kind of interesting because what you see is you see these elongated lights, these LEDs. Each one has a kind of like a letter associated with it. So I got A, B, C, all the way through F, G, and there's 7 of them. And I got these switches over here. Now you don't really have these switches. What I'm circling right now is done by digital logic, but they're just showing you that you can actually turn these LEDs off and on by opening and closing switches. So the switches that actually do this are little microscopic solid state switches that we call transistors. You don't really have to worry about that. Just know that by giving certain switches, by opening or closing certain switches, you can turn certain ones of these diodes on or off. And depending on which ones you have on, down here is showing that you can display the digits that's showing 1 through 9, but if you light them all up, except for the center one, it's actually 0 through 9. So I can display 0 through 9. So one way I can use this on the PLC is to display binary digits. And then there's another device that uses this kind of technology. This kind of code that we're going to talk about in just a second. So the way this is done is inside of the device, the PLC, the computer, there's this thing called a BCD to 7-segment decoder. So over here on the input, you put in something called BCD. BCD stands for binary coded decimal. For your quiz, you need to know what those letters mean. So on the quiz, I'll ask, well, what does BCD stand for? You're going to tell me binary coded decimal. I get all kind of answers for that. So you want to know what BCD stands for. So anyway, anything that uses LCD or LED, they got to have some kind of driver or decoder in it that converts what we call binary coded decimal to drive the 7-segment display or to the whatever device you're going to drive with LCD or LED, whichever one you're going to drive. So that's kind of how this works. And so we want to get into the PowerPoint and figure out what does BCD look like? Let's look at the code. So let me go over to I did upload the files. So let's see where we left off. So we were talking about these codes we're going to look at. There's a couple. I think we got to this one, BCD. So again, BCD, binary coded decimal. And basically, it's a simple way to convert to a code that will drive a LCD or that will drive a LED. So it's really easy to go from a binary to BCD, as I'll show you in just a second. It's really, really simple to go from binary or from base 10 to BCD. We talked about LEDs or devices that you would use with this type of code, but there's also others. And then I think the big thing to remember is this one. This is what you want to know right here. So when we get into what the code looks like, what it is that BCD uses 4 bits to represent each of the digits 0 through 9. I'll show you an example of that on the next slide. So the thing here, right here, the largest number that can be represented by 4 bits is a 9. A 9 in binary, we use that 8421 code. A 9 would be a 1, 0, 0, 1. So I got 8421. This is a 1. That's an 8. 81 is 9. So this is how a 9 would be represented in your computer. So since we can only use 4 bits for BCD, this is the largest number you can represent. The largest base 10 number you can represent is a 9 in binary. This will make more sense on the next slide. So here's a comparison of BCD to binary and decimal. So right here, let me draw a line down here. So here are my decimal numbers, right? And in binary, you can represent these decimal numbers, basically any number of bits. So a 0 is, of course, a 0. A 1 is a 1. To represent this decimal 2, I need at least 2 bits, right? And then 3, I need 2 bits. When I go to 4, decimal 4, I got to have 3 bits. 5, I got to have 3 bits, and so forth. Well, compare that to BCD. With BCD, even though it's 0, we can represent it in binary like this. If you want to represent a 0 in BCD, you must use 4 bits. Even though they're all zeros, you still got to show 4 bits, because what you're doing is you're connecting it to that decoder that I showed you in the previous document. You're connecting physical wires to the input of that decoder, and you're going to feed each input a signal. So you can't leave a wire not connected. That input has to get either a 0 or 1. So since there's 4 physical wires, you got to have 4 bits to move along those wires. Now, the thing to watch out for, remember earlier we said that you use 4 bits to represent every digit in a base 10 number 0 through 9. So what I mean is, I want to be clear, what I mean is, you see how, like right here, let's go to this one. So let's go to 12. So if you look at 12, I'm going to use 4 bits to represent the 1. I'm going to use another 4 bits to represent the 2. So that 1 is hold on a second. I got counted. These are not in order. Okay, so I got the 1, which is right here. I need to make a nicer table. So that 1 is represented here. That's that one. And that would drive one of those decoders that I showed you, and you could light up the number 1. And the second one would connect to another decoder, which connects to another 7-segment display, and that would display the 2. So the secret here with BCD is every decimal digit, you will use 4 bits to represent it. As long as you remember that, you won't have any problem. Now, remember I said that it's pretty easy to go, or I don't know if I said it, but to go from decimal to BCD is really simple. You just take that decimal number, and remember your 8421 code, and you just write each one as 4 bits. So the 7, using 4 bits for a 7, right, will be that. I got a 4, I got a 2 and a 1, that's 7. For 8, well, 8 is, of course, this one. I use 4 bits to represent each of these numbers. So again, on the other side of this, I would have that decoder, and then I can drive a device. I can drive a LED, LCD, or some other device that's connected to the PLC. Pretty simple to do that. So I would say here you want to mark this slide and make sure you study that. You want to make sure that you understand the fact that if I want to represent every binary, if I want to represent a decimal, I don't know why I'm stuttering today. If I want to represent a digit, it takes 4 bits, and then you want to know what the B, the C, and the D stand for. And again, it stands for binary coded decimal. So that's pretty much it for this. Anybody have any questions on BCD? This thing right here, this slide brings it kind of all together. So let's say I have an input device. So I got this input device. Maybe I have something called a thumb wheel. So I can actually dial in a number into my input module. And anytime you deal with base 10 numbers that you're going to input from a device like a thumb wheel or some device, it's gonna have to be in BCD. These things only understand binary coded decimal because you got to represent each decimal digit. And so in the PLC, there's going to be circuitry that converts the BCD to binary. Because even though BCD is a groups of zeros and ones, there's still a binary conversion. So there's an algorithm that will convert the BCD to binary, and then in your microprocessor, it'll process the zeros and ones. And then if you have, like, maybe this is my 7/7 display, I'm going to have some kind of digital readout in decimal. That means I got to go back from binary to BCD, because again, these things only understand BCD. So it just depends on the system, but any PLC will have the capability to convert a BCD to binary and vice versa. And so there's a thing down here that says just kind of read that and understand it. Even though BCD is a bunch of zeros and ones, it's still not just what we call normal binary, and I'm doing air quotes, but you can't see me because I'm not on the camera. So I would say mark this slide, but I mean, there's really none here to remember. I just kind of want you to kind of see how the system works together with the PLC. Okay, so let's move on to our next code. So this next code is called gray code. Gray code. So take a second and just kind of read this. I don't want to read it to you, but I do want to point out a couple things. So just kind of read over this. I want to make a couple points here. Okay, so BCD is a special kind of binary code, but this one is the important. It does not use position weighting. So that 8421 code, it doesn't use any kind of place value. It's just the position of the bits that distinguishes one piece of data from another. The gray code. The other thing to remember is that what makes this important is this one. This one right here. Progressing from one number to another only changes one bit at a time. I'm going to show you that. So there's something called an encoder counter. Says this is good for encoders, but not counters. We'll talk about counters. I don't know if we'll talk about encoders or not. There's a simulation in the software you're going to use where they have some kind of encoder. So I don't know. We might play around with it. We'll see. So you can read this slide, but the 2 bullet points I have circled, these are the important ones. So they call gray code error minimizing code. Error minimizing code. Now I'll speak to that point in just a second. Let me show you what it looks like. So here's BCD compared to binary. So if you look at this and you look carefully, you'll notice, like, if you look at now remember, these zeros and ones are not just sitting inside of your computer or your PLC. You're actually processing these. And by processing, I mean inside of the microprocessor, you're shifting these bits back and forth, and you're doing math, you're doing different things. And then you're also going to transfer those bits into and out of the microprocessor, and also into and out of the PLC. So you're moving these bits around. Either you're storing zeros and ones, or you're moving them around as waveforms that we discussed in a previous lecture. So what happens if you're moving this information around? what's the likelihood that you could have what we call a bit flip? There could be lightning strike, it could be static discharge. You might have some kind of physical situation to cause a bit to flip or noise to be added to the system. So, you know, when you really think about it, and I might have mentioned this example a while back, but I think about my car, how pissed off I get when I go out and my car doesn't start. And, you know, 999 times out of 1,000, I stick my key in the ignition and the car starts. And if you think about everything that has to take place just for a car to start, everything, when you turn that key, everything that has to take place, not just take place, but at the right time for the right length of time, it's a wonder why a machine like that functions at all. Well, a computer or digital device compared to a car, mark that up by order of magnitude. I mean, computers are software systems, and computers these are the most complex systems designed by man. And it's a wonder why, you know, you're moving all these zeros and ones around. If just one bit gets flipped from some kind of environmental situation, then you don't know what kind of effect that'll have. So we talk about error minimizing. We mean, well, how do you know the ones and zeros that you sent is what the receiver received? And the more bits you got to move around and change, the more bits you got to change at a given time, the more the likelihood that you're going to introduce some kind of error into the system. And so if you look at binary, you just kind of go down binary. As you go down binary from one to another, look at all the bits that have to change when you change from one number to another. The biggest one is right here. When you go from here, now this is in binary, that's a 7. And this is the binary for 8. So when you go from 7 to 8, you're flipping all the bits. Anything that's a 1 becomes a 0. Anything that's a 0 becomes a 1, or vice versa. So you're flipping all the bits. You're changing all of them. Well, every time you change a bit, there's a small likelihood that something can go wrong. But if you look at gray code, as you progress from one to the other, only one bit changes at a time. So that's the power, or not the power, but that's the advantage of gray code. So they mentioned that 7 and 8 thing down here. I didn't know I had it down there. So, you know, read this little note down here. This kind of tells you the one advantage of gray code. But this is the big thing, that only one bit changes at a time. So the advantage of that is, as I said, it's considered to be error minimizing code. If you have, I won't say mission critical data, but if you have important data, you got to move down the line. You can do it in binary. There's different ways you can do it. But by converting it to gray code, then you can code it in a way to where there's less likelihood of an error, because you're not flipping all these bits on and off. Okay, so you want to mark this slide, just kind of know the advantage of gray code, that one bit changes at a time. And the importance of that is, if I have some kind of information, digital information I want to move around, and this is a way to minimize the possibility of introducing error into the system. So that's gray code. The other one is ASCII. Now this is actually really important here. ASCII is American Standard Code for Information Interchange. If you've dealt with computers before, you probably heard about ASCII code, called ASCII or ASCII 2 or something like that, ASCII code. What this is if you think about letters of the alphabet, you got A through Z, but you also have uppercase A through Z and lowercase A through Z. You got to be able to move those around and represent those as digital information. And not only that, what about the other characters on the keyboard, like the exclamation point or a comma, or basically any character on the keyboard? Excuse me. And some characters are not printable characters. Like, remember, you know, when you turn your computer on, it makes a beep. That beep has a binary code associated with it. So basically, every alphanumeric representation of something has to have a binary code to correspond to those alphanumeric characters. And so this is what ASCII does for us. So if we look at that, I think I got a, let me go off of this. I think I got a, did I put it? Yeah. Okay, look at this chart. So now if you look at this closely, oh damn it, hold on guys, my lights went out again. I guess I won't have to worry about it after today because I won't be in this room anymore. I'll be involved with. Anyway, if you zoom in on this, zoom in on it, and take a look at this. So what you have here is you have a decimal representation, you have a binary representation. Now you know what this is. You have octal and you have hex. Okay, so what are we representing? Well, let's come over here. So like right here, this is the @ sign on your keyboard. And so on your keyboard, if you hit Shift 2, you get the Shift key and the number 2, that's that @ symbol. Well, here's the binary representation for the @ symbol. And if you convert that to decimal, this is what you get. If you convert that to octal, this is what you'll get. Convert that to hex, this is what you'll get. And remember earlier when I said that even though we know that digital devices only store binary, the reason you want to know hex or octal, these other number systems, is if you're actually working with this ASCII table, you don't want to have to remember these binary codes. It's much easier to remember a hex value of 40 or octal value of 100 than it is to remember these codes. But basically, you'll see if you look under the column that says ASCII, every single character on the keyboard of a typewriter, not a typewriter, a computer, or even your cell phone, when you type the letter A is so like we said about a number. When we said in the last class that when you enter the number 12 into your cell phone, you're doing a calculation with it. So you bring up the calculator, you enter 12. When you hit enter, what goes into it is a 1100 base 2. That's the 12 to a computer. Well, you can say the same thing for letters of the alphabet, upper, lowercase. You can say the same thing for any symbol on your keyboard. Any symbol is going to be represented as binary. And these are the binary equivalents. So this is the actual code. So you can actually code out a whole message if you wanted to. So remember your delete, look at your delete key. The delete key on your keyboard, there's a binary representation for that. The computer understands this number and that it means delete. Now let me show you, let's see, is it on here? Okay, right here. Look at this right here. So when you deal with numbers, the best way to think of this is like this. Remember I said a 12, or let's use a 9. So the binary equivalent for 9, binary number for 9 would be a 1001. But look at what they have for 9 here. They have for 9, they have this long bit right here. It's not 1001. Because this 9 right here is an alpha version of 9. The way to think about it is this. If it's going to be stored as an actual binary number with position weighting, that's any number that you can do math with, right? If you were typing out a Word document and you type the number 9, where you type that number 9, it's not going to enter 1001. What's going to be entered is this ASCII code for 9. So there's an alpha representation of the digits 0 through 9, and then there's the actual number representation. So don't confuse these. So this is kind of interesting if you look at the table. And then, so basically, everything on the keyboard is represented here. But they actually have, I think it's, God, I can't think of the name of it. One is called Unicode. There's one that takes into account, there's some keyboards that don't use English letters, like they might use Chinese or some other language. So there's a bigger table like this that takes into account basically all the languages, all the major languages. But I think the most used code for representing alpha characters is going to be this ASCII. Okay, so nothing you have to know here. You know, I might do something like give you an ASCII, maybe write out using octal or hex or something, and tell you it's ASCII code. I might have a message for you or something like that. Be able to use this chart to convert a code to an ASCII character. I don't know. I'm not saying I'm going to do that, but it's nothing to study. Just kind of know that this document exists and make sure you look at it. Anybody have any question over ASCII? Okay, when you get into hacking computers, and there's certain, you can do a lot of damage by knowing this. If you know a little coding and ASCII and how to do things on network, when you get into these codes, you can do some damage if you wanted to. So anyway, let me keep going. Let's see, binary codes, and where were we? We're almost done with this one. So we got ASCII, and so just kind of read this and just be familiar with the table. The numbers are the same value, 9, so but just begin. Yeah, so somebody said that the numbers have the same value, but they just put the numbers in front of it so that it fills out a whole byte. Okay, so that looks like that's the case, but still just know that they did that, and I guess it's smart to do that, but that ASCII code does not use position weighting. I think that's the thing to remember. Even though the characters are the same, they added those 4 bits in front of the 1001. It still doesn't use position weighting. It's just the position of the bits that distinguishes one character from another. So I think that's the point to make. And then there's this encoding and decoding, and the letters are numbered. So, but this guy's in the codes. Look at this. Who is that? That's Nicholas. He's fascinated with that table. So yeah, it's interesting. Yeah. Honestly, I never looked at it that close. When I was a student, we did some stuff. I don't know what. It was some programming class, and we had to send ASCII code, look at some ASCII code, and do some. I want to cut some stuff that was probably not good to do. But it's been so many years ago. I graduated from college in '96, so you guys weren't even born. Some of you weren't even born. Then I got 3 degrees, so I'm even older than you think I am. So anyway, yeah. So there's this chip, this device that actually you can input a decimal number and you can output something else. You have these encoders and you can decode. You can encode and decode. So anytime you're going from binary to another number system or vice versa, there's always this encoder decoder. We talked about ADC, analog to digital code, or DAC, digital analog converter. So you can convert from one to the other. There's always some kind of encode decode. They're used in pairs. So nothing to know here. Just if you're wondering how does this thing work inside, there's circuitry to do all of this. You don't have to think about it. You just push buttons. But the computer has all of these encoders and decoders built in it. So I want to say that, let me go back here. I think that is it for this one. I lost my, hold on a second. I lost my place here. This thing gets, there we go. This thing gets stuck sometime. It doesn't want to go. So you can kind of read the rest of this. I don't think there's anything I want to say here. I do want to say one thing about something called parity. So what is parity? So this is actually pretty important. So important, I'm not going to talk about it. I'm going to make it a homework assignment for you. But just kind of in a nutshell, it's kind of what I said earlier. Let's say I'm the sender of some kind of information and you're the receiver. How do you know what you got is what I sent? How do you know that? So you got to have a way to verify. Sometimes you don't care. I mean, but if it's what we call mission critical information, then you got to care. So parity deals with that. How can we transmit digital information, and how do I know if what I sent is what was received? So I won't say any more about it. I forget which homework it is, and I actually forgot to activate your homework, so I got to get that activated. But eventually, you'll get to a homework where you have to use parity. So, anybody have any questions over number systems or codes? Jacob, you know, you can't see yourself. I wish I could show. You just look so grand, like Jesus Christ himself, without the light behind him. It's just, he's the only one that's got his camera on, and it just looks kind of like royalty. All right, so now we want to know, okay, if computers work in binary, how do they do math? How do they do arithmetic? What goes on inside of the brain, the CPU, where it can do arithmetic? And so we want to look at basically binary arithmetic, and we're not going to do division. You could do division, but we're not going to do division, and you're not going to have to do any of this. We just kind of want to know what's going on inside the machine. So we have these, I think you guys can see over here, we have these rules for like addition. And so these are now normally I write a binary number, I have to subscript it with a 2, but I'm just gonna, you know, these are binary. So like if I take a binary 0 and a binary 0 and I add them, I get a 0. If I take a binary 1 and a binary 0 and I add them, I get a 1. I take a binary 0 and a 1 and I add those, I get a 1. A 2. Now remember your 8421 code. So you want to have that off to the side somewhere. 8421 code. So if I want a 2 would be a 1, 0 base 2, right? So if I add a 1 and a 1, I get a 2, but I can't write it like that. I got to write it like this. So a 1 and a 1 would be a 1, 0 base 2. So I meant to tell you this at the beginning. Damn, we're going to be running out. I feel like I'm never going to get caught up. Get a sheet of paper out. And I don't know if you guys download the PowerPoints, but don't look ahead because I just kind of want you to do this kind of off the top of your head. We're going to practice some of this. So get a sheet of paper out, get a pencil out or pen, and I'm going to put some numbers on the board, and I want you to add them up in binary. So you want to write these down because I'm going to erase them. And then I'm going to put some numbers up here, and we're just going to practice adding, subtracting, multiplying these numbers. I'm going to go through it. I'm going to try to finish this, guys. I don't know if I'll be able to. We're going to kind of move kind of quickly. So go ahead and get a sheet of paper out, write these down, and I got some examples right here. I'm going to put on the board, and I'm going to kind of move quick. If I'm moving too fast, you want to write your 8421 code down so you have it. And I'm going to put some numbers up here. What I want you to do is apply these rules and add. So then the first one is this. So we got a 1, 0, 1, 1, 0. Again, these are on the PowerPoint, but don't look at it. Don't. If you got your notes out, don't look at the PowerPoint. I just want you to do it by thinking about it. We got a 1, 0, 1, 0. I have to erase this. Then we got a 1, 1. And then we got a 1, 1, 0, 1, 0, 1, 1, 0, 0. So go ahead and add those up using those rules. So I got a 101, 0. Okay, I think I got these right. I'll give you just a minute to do that. Now, can somebody tell me what that is in decimal? What is that in decimal? You got 1, 2, 4. So a 4 and a 1 is a what? This is a 5 base 10. This will be a what? Are you guys listening? Or you're just not? You're not talking.
I'm just in the middle of just doing the problems.
Okay, my bad. Let me put this back up so you can see it. You can do it faster if you have this up. 8, 4, 2, 1. So this is a 1. Just kind of. So this will be a 2, right? So when I add these, I should get a 7. So let's add these real quick. I'm gonna make this blue. So what is a 1 and a 0? If I add a 1 and a 0, I'll get a what?
A 1.
A 1 and 0 is a 1. A 0 and a 1 is a 1. And then I bring down this 1. So I got a 4, I got a 2, and a 1. If you add that up, you get 7. Okay. So that one works. Right here, again, I got a 0 and a 1. That's a 1. Now right here, look at this. Remember we said if you have a 1 and a 1, then that's a 0, and you got that carry over here. A 1 and a 1 is a 2, and base 2 is written as a 1, 0. So what you got to do here is you go a 1 and a 1 is a 0, and this 1 right here is called my carry. I bring it up here like that. So I got 1 and a 0 is a 1, and I just bring down this 1. So I got 8 and I got 2, 8 and 2, I got 10, and that's a 3. Should be 13. So I got 8, 4, it's 13. So this works. So this is kind of, the computers do this. They do it using and or not gates, but they do exactly what we're doing here when they're doing math. What about this big one down here? So I got a 0 and a 0. I'm adding those. That's a 0, a 1, and a 0 is a 1. A 0 and a 1 is a 1. I got this thing again. A 1 and a 1 is a 0, carry 1. And a 1 and a 1 is a 0, and I write the carry like that. See it? So I think this is 26 base 10. This is 12 base 10. You add those up and get 38 base 10. I went through that kind of quickly, so is everybody okay? This is the other part I don't like about online is I can't especially since you guys don't turn your camera on. Okay, Jacob said, yeah, thank you for the feedback, Jacob. All right, I had to give Jacob extra credit for turning his camera on and feeding back and all of that stuff. All right, now let's do subtraction. So I got my rules. All right, so we got 0, 0, we got 1, 1, take that away. We got 1, 0, take that away. Now this one, we got, this is this is the number 2. Remember, I write a 2 like this. I want to subtract 1 from it, like that. So when in any number system, 0 minus 0 is a 0. 1 minus a 1 is a 0. 1 minus 0 is a 1. Now right here, I got a binary 2 and I'm taking 1 away from it. What I have left over is a 1. So addition and subtraction rules are pretty easy. Okay, so I'm going to put some problems on the board. Let me change to a different color. I'm always using black and purple in honor of Prince. Some of you probably don't even know who Prince is or was. He passed away. All right, so my examples are here. We got a 1, 1, like that. Subtract that. We got a 1, 1. Subtract that. And then we got a 1, 0, 1. Subtract this. Okay, so go ahead and take a minute and do that. Oh, cool. Christopher knows a little bit about Prince. I'm shocked. I just don't think there's any more. I think now we have performers. There's a difference between an artist and a performer. And so now I think nowadays we have a lot of performers, but they're not artists. And what the heck is mumble rap? I was in a car with this guy as a kid, 16-year-old, and he had his phone playing some kind of rap song, and I couldn't understand. The guy sounded like he was having a seizure or something. He said, that's mumble rap. I said, what the hell is what's mumble rap? You pay for this stuff. I can't. It's just I don't know what happened to music and creativity and all of that stuff. So maybe your generation will be the ones that bring creativity back. Because right now we don't have it. Raspberry. All right, so we have a 1 minus a 1. That's a 0, right? 1 take away 1 is a 0. We have 1. I'm sorry, I said that wrong. 1 take away 1 is a 0. 1 take away 0 would be a 1. That's a base 2. This is a 3, base 10. This is a 1. I take the difference, I get a 2. Pretty simple. Here, same thing. I got 1 take away 0, 1. I have a 1 take away 1 is a 0. In base 10, this is a 3. This is a 2. You subtract these, you get a 1. So binary 1, that works. Now this one, let me move this one up a little higher, because this one, I want you to really get this one. Let's do this one up here. So we got a 1, 0, 1. We got a 0, 1, 1. So if I was doing, let's say I was doing 5, 2, 4, and I was subtracting from it 36, not 36, 31. Let's say I was going to do that. If I was going to do that, I said, all right, I got 4 take away 1. Well, that's 3. I got 2 take away 3. Uh-oh, I can't do that. So what do? I come over here. I got to borrow 1 from here, which means that gets knocked down to a 4. So that's a 4. And that the 1 that I borrow, here's the 1 that I borrow, but it's really not a 1. It comes over to this column as a 10. So this is really a 12 minus 3. You borrow 1 from over here, it comes over as a 10. So I got 12 take away 3. You do the same thing over here. You do exactly the same way. You say I got 1 minus a 1, that's a 0. I got 0 minus 1, that's just like this one. I said I can't do that, so I got to come over here, change that to a 0, borrow 1 from it, but that 1 comes over, this right here, that 1 comes over as a 1, 0. And so now I got 1, 0 minus 1. 1, 0 minus 1, that's that 1 we talked about. So I borrow 1, it comes over as a 1, 0. So I got 1, 0 minus 1, there's a 1 left. I got a 0 minus 0, it's a 0 left. So that borrowing's done the same way, but you're doing it binarily, if that makes sense. So if you got that, let me give you another one. If you got the borrowing thing, I want you to do this one. Guys, I might run out of time. I might go over just a little bit. If you got to sign off, you can go ahead and make sure you watch the video, because I'm going to try to finish this. So I want you to do this one. Do 1, 1, 0, 0, 1, 0, 1, 1. Now, if you do sign off, make sure you go back and watch this part of it, because this is important. So do that one. Go ahead and subtract that one. I'll give you a second. Because you got to borrow here a couple times. Give you a couple more seconds. I'm not trying to, I don't do well under, I found out in that accounting class, I don't do well under time constraints, but I got to put you under one. Okay. So what we got to do, we got to borrow a couple times. 0 minus 1, I can't do that. I can't, what I got to do is I take this, I got to borrow 1 from here. This is 0, so this is going to come over as a 1, 0. But I really got to get over to that column. So now I got a 1, 0 I got to borrow from. I'm going to borrow 1 from this 1, 0. When you have a binary 2 and you borrow 1 from it, you still have a 1 left. And the 1 I borrowed comes over here as a 1, 0. So I got 1, 0 minus 1, that's a 1. I got 1 minus a 1, that's a 0. I got 0 minus 0, that's a 0. And I got 1 minus a 1, that's a 0. Now you might, I only got a couple minutes. I want to show you the next part of this. So you might have to go back and watch this on the video, but make sure you can do that. But what I really want, remember we talked about negative numbers, and we talked about the sign bit, we talked about ones complement and twos complement, and I said sign bits and twos complement are the most important. Well, think about this. If you're subtracting say you're subtracting 7 minus 3, you know the answer is 4. But you can do it another way. You can do this in terms of addition. You can say 7 plus the opposite of 3 equals 4. So I can do direct subtraction, which is what we've done here, or I can add the opposite. And the opposite in binary is the 2's complement. And I can get the same answer. So another way to do this would be like this. This is represented by this, but if I want to do it this way, I say, all right, I got a 1, 1, 0, 0. And what I want to do is I want to add the opposite. But what is the opposite of this? So I got to take a 1, 0, 1, 1. The opposite is going to be the 2's complement. 2's complement says that up to and including the first one, you leave it. And everything after the first one, you take the 1's complement. So that goes to a 0, that goes to a 1, that goes to a 0. So I'm going to add to this 0, 1, 0, 1. And now I'm not subtracting anymore, I'm doing this. So I go, well, 0 and a 1 is a 1, 0 and a 0 is a 0, a 1 and a 0 is a 0, carry 1. A 1 and a 0 is a 0, carry 1. A 0 and a 0 is a 0. And you may say, well, hold on, Singleton, they don't match, but what you do is you throw away the carry. So it turns out, and I wish I had more time to talk about this, it turns out that computers, when they do subtraction, they do it the 2's complement way. The way that there's something inside of a digital device called a arithmetic logic unit, and the way it works is so fascinating. It just uses some simple gates, and I wish I had time to dig into that and show you and tell you more about it. But just kind of look over the slides. Now, how much time do I have? I got like 1 minute. And Friday, if I'm at my mom's house, I won't have a board. So we'll just have to do multiplication. I'll just show you the pictures of it. You know what I might do? You guys, if you have to sign off, go ahead. I'm going to just keep talking. That way, if you got to go back, you can watch the video. Let's do that. So if you got to go ahead. If not, I'm going to take about another 5 minutes to finish this up. And you can always go back and watch the video. Because we're almost done with this. And I just got to go through the PowerPoint real quick. So if you got another class or you're tired of listening to me talk, go ahead and sign off. I'm going to keep teaching. I got that accounting class in about an hour. So I got time. I'm going to go over. We got about another 5 minutes. So I think we can be okay. So last one I want to do is multiplication. That's really, really easy. So we got 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. And 1 times 1 is 1. So look how easy this is. If I have a 1, 1, so this binary, so this would be a 3 base 10. This would be a 1. If I'm multiplying that, gives me a 3. So the way you would do that is, when you go ahead, I'm moving so fast, you go ahead and you do it, and then we'll talk about it since I have a little bit of time now. And this is actually pretty easy, this one. I go 1 times 1 is a 1. 1 times 1 is a 1. So I got a 3 times a 1 is a 3 in base 10. A 3 in base 2 times a 1 in base 2 gives me the 3, gives me the same thing. That one's kind of boring. This other one though, I got okay, now I'm multiplying 3 times 3. So you got 3 times 3. So that's a 3 and a 3, we should get 9. So you go ahead and you do it on your paper. And my light just went out. So let me go turn it on while you're doing it. Back on. That's a 3, 3, 9. And if you're thinking about this the right way, the key here is you got to shift over when you get to this second multiplication. You got to shift it. It's like you're doing regular multiplication. You got 1 times a 1, that's a 1. 1 times that 1 is a 1. When you do this one, you got to put the product you got to put over here. 1 times 1, you got to shift it over a column. And then 1 times 1 is 1. And then you add these, just like in regular multiplication. And so this one just drop down as a 1. This is a 1 plus a 1 is a 0, carry 1. You got a 1 and a 1 is a 0, carry 1. So this is in my 8421 code. That's an 8, that's a 1, that's a 9. So multiplication is just simple as heck as long as you remember to shift over. And I think, yeah, we covered everything. Now, let me take now we can fly through the PowerPoint because pretty much everything I did is in the PowerPoint. Let me see how many people I said. I got 13 still. Okay, cool. Let's do this real quick. I promise you this will just take a minute. And because we talked about everything. Uh-oh. You know what? I didn't upload it. I'm sorry. I got to upload it real quick. It just takes a second. All right. So here we go. Binary arithmetic. So again, the whole point of this is not that you have to actually do this, but the CPU and PLCs contains there's a part called the arithmetic logic unit. And you can do basic math with PLCs. So how you do math if everything is in binary? Well, I just showed you on the board. You can actually do math in binary. And so that this one we're not using division. We're just using addition, subtraction, where the result is positive, and multiplication. But really, you can do any of this. You can do subtraction where it's negative. You can do division. We just not getting into that. But you can do it if you wanted to. It's not that difficult. So here's the rules that we talked about, and these are the examples. We did each of these examples in class, so you can go back and review this slide, kind of see what's going on. These are our rules for subtraction that we talked about. And these are the subtraction examples. And then here, this is kind of when you're doing the 2's complement subtraction, you want to just kind of read this kind of walks you through the steps. And then, did I skip a slide? This is the actual example we did. So the first time we did it, oh shit, I'm sorry, guys. I got to edit that. I'm not supposed to cuss in class, but I got myself in the bind here. I guess I can edit that cuss word out. I was trying to show you the example, this one. This is what we did in class. You did it by direct subtraction. That's where you had to keep borrowing. But it's much easier to add the opposite, to do the 2's complement. Just remember, on this, you throw the carry away if there's a carry bit. So you can always look on YouTube and kind of see this stuff. It's pretty simple. I mean, it's not rocket science. The whole point of this is all done by a circuit in the device called, this is an adder. It turns out that they can pretty much, and I wish I had more time to go into this, but I don't. But you can do, even though I showed you addition, multiplication, and we didn't do division, you really can do every single thing with an adder, with just one single adder. So I don't know. Maybe if I have time, maybe I'll talk about this. But it's just amazing that you can have this one chip and it can do all the 4 operations: addition, multiplication, and I don't know. I guess there's nothing else to say about this. So guys, anybody have any questions, comments? Thank you so much, the 11 of you that hung in there. Let me see your names. Okay, got anonymous caller, got Ben, Bradley, Connor, Jonathan, Josh, Kyle, Nicholas, Ray, and Sean. Thank you guys for hanging in there with me. And have a great rest of the day. Stay safe. Don't get into that ice storm. Stay safe. And remember, if the school is closed, we said we're going to shift to online. We'll pivot to online. I'll see you guys on Friday and see you face-to-face on Monday. Have a good rest of the day. Oh, Nicholas, I got to. All right, I'm gonna decode that. Let me go and grab it. I'm going to, is it gonna let me copy it? All right. I'm gonna decode that, Nicholas. I'm gonna send that to myself and figure out what the heck did he say. Let me send that to myself. That was pretty cool. Okay, I'll text myself. I see my nephew just texted me. I'm gonna text it to him. Telling one of my UC students sent me this and asked. He's a brainiac, so he's gonna try to figure out what you said. Okay, well, thank you, and I will see you guys later. That was fun.
Hold on. Do you hear me or no?
Oh, Brad, I can hear you.
Okay, that's nice.
You have a question?
Let's see. No, I was fighting with my stuff to get it working. I always have so much trouble getting my computer to send my camera and my microphone through to my what do you call it? Like web browser. So.
Let me see if I can see you.
Hey, you should be able to right now.
Hey, man, look at that background. I love it. I love it. Did I see your background before?
Yeah, I think you commented on my shoes one time.
And, I didn't see the brick wall though. I like the brick wall, and I'm a real estate investor on the side. So you play the piano?
I do.
Really?
Yeah, I do.
Oh, that's exciting. That is so exciting. Look at that, beautiful.
This
is that an apartment?
I'm actually on Shortvine Street.
Oh, I love that exposed wall. That is beautiful. Oh yeah, you got a bird's eye view, don't you?
You see where I'm at now? You recognize this?
Yeah, this is beautiful. You got a nice place there.
Yeah, it's pretty nice. It's got the whole.
That's a good spot. Oh wow.
The whole setup here.
I love it. I love it, love it, love it. Look at it. I love it. You're living like a king.
I think I have one for the guests too.
I love it. That is really, really nice.
Yeah.
Really nice.
Oh, now I'm out of focus.
Why do you have such a professional looking microphone?
It's like this is like my hobby. This is where I put all my money. So.
What do you do?
Like for work, you mean, or for this?
When you say what's your hobby, what do you mean? What do you say is your hobby?
Oh, just like having, well, I do a lot of gaming and I spend a lot of time online, and I guess I want to sound nice while I do it. So I'm not like singing or anything, but.
You sound really, it sounds really good. That mic sounds good.
Yeah, it sounds, yeah, honestly, if you need an audio setup, I could give some recommendations. So, but yeah.
Now that boom, what kind of mic is that?
It's the type of mic is a dynamic microphone.
Okay.
But the brand on it's Rode. It's intended for like podcasts and stuff.
Can you spell that for me? R-O-D-E, or how you spell Rode?
Yeah, it's R-O-D-E.
Okay.
I think it's like on the thing here, and then the arm is also from them, but obviously sold separately. But it's nice to be able to move it around. So.
The only reason I'm asking is the nephew I just mentioned who just texted me. We're gonna kind of do this. We're gonna do a YouTube channel. It's not gonna be a podcast. We're gonna try to do some tutorials. But I like to have a nice microphone like that. So.
Yeah. No. Honestly, send me a message or something, or maybe when we're back in person, we can talk about it some. I do a lot of this stuff, so it'd be fun.
Okay, like when you say a lot of this stuff, what do you mean? Just kind of putting together these systems for yourself, or?
For myself, but also I've had people buy them off of me and stuff. Like I'll put together whole gaming setups for people, and I usually for gamers or whatever. But one time somebody who was doing sound design, but I'm not an audio engineer or anything. I'm obviously here studying mechanical, but
you could put together a small studio, right? You know what pieces you would need to put together.
I know enough about the hardware to find what you need and stuff, especially for more budget oriented stuff. I don't know about professional level. I'm not a professional, right?
Okay.
But
And I think you're exactly what I'm looking for, to be honest. We're gonna talk we'll talk when we get back face to face. And
absolutely.
I will, yeah, and I would, I really don't mind. I'll pay you for whatever you. Hold on, let me
Oh,
unrecord this.
no
I don't want
worries.